Okay, everyone, it's 2:45. I'm going to get started. I do have some very good news. It's only an hour until the next coffee break. So hope you can all look forward to that. And in the meantime, I hope you'll care about my talk just as much. I know that we have a lot of kernel hackers, systems programmers here, and one thing that really matters to us is performance. If any programmers are going to, count instructions, count cache misses, it's going to be us. So caring about performance, we're going to be making a lot of use of a piece of hardware called a PMU, or Performance Monitoring Unit, that allows us to efficiently count instructions, branches, cache misses, cache hits, things like that. And specifically, since this is KVM forum, I'm going to talk about using the PMU inside KVM. I'm talking about optimizing the vPMU on ARM, how I've been working on that, and specifically how I've been doing that with partitioning of event counters. So a little bit about myself. My name is Colton Lewis. I've been working at Google Cloud's KVM team for about 3 years now. It's been a very great experience, and I've been humbled to work with so much talent inside and outside Google. Like no other work I'd rather be doing. So just giving a brief overview of the agenda for my talk. I'm going to start with a brief introduction to the ARM PMU, the problem I'm working on, and the solution, just a high-level overview. I'm going to give a summary of the main implementation steps that I've taken. I'm going to discuss the current status of this project, and then open the floor for questions. Okay, so talking about project motivation, working in Google Cloud, customers pay us for compute, and they would like to pay us less for compute. So they really need to profile their software, and that means they need to use the PMU to optimize their compute use inside our VMs. And more importantly than that, some OSs like Windows, of course it's Windows, needs PMU counters to even boot. And currently, how KVM handles the PMU is it emulates it through the host perf subsystem, which is fairly expensive. And the cost of the overhead comes from needing to create host-side perf events for every guest use of a counter, which is a lot of bookkeeping. And then there is some lesser but still significant overhead of KVM needs to trap every access to a PMU register. So having established this motivation, what can we do about that? So the solution I've settled on is partition the counters into a host set and a guest set, with the idea being that the host perf can continue to manage the host set of counters, and we reserve the guest set to just be more directly managed by the guest where it's possible to do so. This allows the guest to skip all that host side perf overhead and some of the KVM trapping overhead as well. Now, if you're more familiar with the x86 side of things, they've also been working on improving their vPMU, and they went with a different approach. They did a mediated pass-through vPMU. So you might ask, why elect a different path for ARM? And the primary thing is ARM has hardware support that makes a partitioning solution both more efficient and easier to implement. And if you have any experience programming, you know those two qualities don't come together very often. So it's usually a good choice to take those. Specifically, the hardware feature these optimizations depend on is called vPMUv3. If you were here for Mark's talk, I'm going to be touching on some things he brought up since they're relevant. Specifically, the partitioning is well supported in hardware by a register field called HPMN. And how HPMN works is it defines a pivot point. That's just a number between 0 and the number of counters on the host. And everything, you set that value, and everything below that value is accessible to the guest, and everything above that value, all the counters above that value are accessible to the host only. So to have a nice diagram showing the change in operations, if you look on the left, you see the old operation. You have the guest perf subsystem. All of the register accesses are trapped into KVM. And then KVM needs to create perf events in the host perf. And then the host perf actually manages the PMU hardware. So you see that's several steps of indirection. It's not very efficient. So a better solution, what we can do instead is just cut out the host perf subsystem almost entirely and allow the guest perf some direct access to the PMU so it can manage its own counters itself. So a short digression for those of you that aren't familiar with how the ARM PMU hardware works. As I said, these optimizations depend on ARM PMU v3 or later, which was introduced and is strongly recommended since ARM version 8.0, which came out in 2011. So this is an extension, but it is a very commonly implemented one. And this architecture provides a lot of counters, a cycle counter plus 31 general purpose counters. In the server hardware I've worked with inside Google often has like 10 to 20. This is another point in support of a partitioning solution where you can partition without taking too many counters away from the host or not having enough for the guest. And the basic function is just you have some auto-incrementing, I'm not going to read all that, but you have some auto-incrementing counter registers. You program them, they count up, they overflow, they might generate an interrupt. That's how that works. Okay, so now I'm going to discuss what implementation steps I've taken. The first thing that's not on here, but I guess you could call it step 0, is I did need to reorganize a lot of the PMU functions and headers because there was a lot of stuff inside the emulated PMU implementation that was really generic to any PMU implementation. So starting with a good base to work from, move some functions around, that's the first few patches. The next couple of patches, is working with the host PMUv3 driver, specifying that partition pivot and making sure the host driver stays out of the side we're reserving for the guest. Step 2 is allowing for the faster register access. We're untrapping via fine-grained traps where that's available. You might remember that from Mark's talk as well. But even when fine-grained traps feed FGT is unavailable, we can provide an alternate fast path to avoid a full context switch into the KVM. Then step 3, we now have some new register state that's under control of the guest. So we need to make sure that is context swapped in and out on vCPU load and vCPU put. Then the next part is tracking the interrupt handling, tracking when the guest counters experience an interrupt and making sure those interrupts are appropriately injected into the guest. And then the last step is putting some UAPI controls on top of it so user space programmers can use it. So first, talking about the host PMUv3 driver. The first thing I did is I used a module parameter to set aside some counters statically at boot time. This wasn't my favorite thing to do, and later, if someone's more familiar with the internals of the perf subsystem and has ideas for how to cooperate better with it, I'm all ears. But as far as I know, the perf subsystem assumes that available counters don't really change after boot. So we have to grab them before the host perf subsystem has a chance to use them, because once the host perf is using them, we can't rip it away. So more, specific implementation details. There's a bit mask which informs the driver of available counters. You modify that to say, okay, the counters we're reserving for the guest isn't available. And then there's some changes to make the PMU-wide operations, such as reset, make sure that only affects the host counters. Then we have the fast register access. So we're programming that HPMN value, which is what gives us our hardware enforcement that makes sure the guest can't access the host counters at the hardware level. Then with the fine-grained traps, we're untrapping some select PMU registers, specifically untrap the registers that are safe, untrap the registers that could not possibly allow a guest to profile information about a host. Without the fine-grained traps, the only other option, which is what KVM does currently, is to trap every PMU access in bulk using the TPM bit. But we can still gain some performance there by putting those safely untrappable registers in a faster trap handling path. As an example of some registers that need to remain trapped, the event type registers stand out because KVM has a PMU event filter that allows a VMM to control which events a guest is allowed to access, is allowed to count. So we need to keep that trapped so we can enforce that filter. That also controls things like which EL levels can be profiled. Then the context switching. So the untrapped guest partition registers, They have to be saved and restored on vCPU load and vCPU put. Now, that does incur a cost of you have a couple registers that are now being swapped in and out on every vCPU load and put. But I have implemented a way to do this lazily. So guests do not pay the cost of doing this unless they've actually accessed PMU registers and thereby shown that they are using the PMU. This is a fairly simple mechanism. You just start off trapping the first PMU access, and once that is hit the first time, you reconfigure with the fine-grained traps and load the new configuration. This is also another boundary where we have to enforce that KVM event filter, because it could have been changed while the guest wasn't running by the VMM. So the fourth part was interrupt injection, and if you remember from Mark's talk, he said the interrupt virtualization was 90% of the work, and from my experience on this is probably the highest ratio of time spent getting it to work to actual lines of code. And part of the reason for this is we have a bit of a delicate dance to perform, because on a host interrupt, that actually still hits the host interrupt handler. So we need to handle those bits as normal, but make sure we still have enough context associated with the vCPU that when we re-enter the VM, then we know to inject that interrupt. And you might ask, why are we hitting the host interrupt handler at all? And this is a limitation of current ARM hardware. They use one interrupt line for all PMU interrupts, whether it belongs to a VM or the host or whatever. That may one day change, but it is not today. So on the next, so the basics of how this works is very similar to how the emulated PMU injects an interrupt. It computes whether there's been an overflow, and on the VM reentry, it injects the PMU IRQ into the guest using the existing VGIC interface, the interrupt controller interface. So the main thing I had to do here was provide a new function that computes the overflows when we're using a partition PMU. And then the existing machinery handles the injection for me. Then last but not least, yeah, I've got plenty of time. Last but not least, we have the UAPI, and it's fairly simple at this point. Define an ioctal kvmarm partition PMU and an associated cap that allows user space to enable or disable this capability. Also, technically part of this interface, but belonging to a patch Mark posted earlier this year. The number of guest counters that's actually exposed, the number of counters actually exposed to the guest is stored as a PMU device attribute, and so is controllable by a VMM. So all I have to do is make sure that number doesn't go over the limit set in the PMUv3 driver parameter I discussed earlier. So now, the interesting part, where this project currently stands, the current status. So testing-wise, I have an implementation. I've done quite a bit of manual testing showing perf stat and perf record, running and measuring events accurately in every case I can think of, including like very high sample rates, multiplexing many events among a smaller number of counters, and using guest and host perf simultaneously. There's also a self-test already upstream called a vPMU counter access, and my current upstream series includes the changes to run all of the tests in that self-test with the partition PMU enabled, and I do have that passing. Additionally, there's also an internal Google's vPMU test, self-test, which I'm still working on at the moment. That's much more comprehensive. So the reason you're all here is what performance improvements do we get from this new approach? And they are quite substantial. As one example, using perf stat in a guest on SpecInt 2017 spends 93% less time in the host kernel because we're doing a lot less trapping to the KVM. We're doing a lot less overhead in the host perf. And this results in the total benchmark score going up 6.5%, which is very huge considering we're talking about perf overhead. And SpecInt is a very CPU-bound thing. Some other examples of performance improvements. So perf record inside of VM can now handle much higher sample rates. Before the internal governor would kick in at about 10% of the maximum host sample rate. Now we can get up to about 80%. So that's a big improvement. Perf record also handles multiplexing much better. Multiplexing being when you have more events than counters, so you have to switch the events in and out of all the counters. So as one example of a test I did 15 events on 10 counters. It was specifically, I looked at programs like gzip and stress and G and saw you improve total runtime by 24% lower total runtime. If you're interested in more of the specifics of the commands and testing I did, they're in the V1 cover letter linked there. So as for current development progress, V4 of my series has been posted upstream. So I'm excited about that. Also, I'm working towards deploying this internally to GCE, but it's not quite there yet. And yeah, it looks like time for questions. I also have a couple of topics to discuss if there aren't very many questions. Yes. Yeah, you. Mm-hmm.
So do we assume that the pivot is the same across all vCPUs?
So you said the question is, do we assume the pivot is the same across all CPUs? And the answer is yes in the normal case, but there is also error handling to make sure, because ARM has the possibility for heterogeneous CPUs in case we can't actually program that pivot for specific CPUs. Yeah. Yes. Yeah, so your question is, did I measure any skid when going from the emulated PMU to direct access? So can you explain a little bit more what you mean by skid?
I mean by you stop, you basically have the interrupt that signals the event. Basically, you handle it past the point where the event fired. Your counter keeps counting. So that gives you basically the time it took for the interrupt to be handled. My question was whether you would see any reduction of that delta.
Oh, you're asking if I saw a reduction in the time it took to handle the interrupt.
Yeah,
Okay. Yes, I didn't include it here, but I did make some informal measurements, and I saw a very marked reduction in the amount of time it took to handle an interrupt, going from thousands of nanoseconds to hundreds of nanoseconds. Mm-hmm. Yep. Oliver?
Have you thought about how this is going to interact with nested virtualization?
Could you repeat that?
Have you thought about how this is going to interact with nested virtualization?
I have thought about that some, but as far as knowing if this will work as is with nested virtualization, I do not know that yet. Mm-hmm.
There's elements of PMU emulation that you still will need
Mm-hmm.
you can't throw the entire thing onto the site. You might be able to carve out some of the EL2 specific stuff.
Okay. Yes, Will.
So you were talking about the pivot being specified on the module parameter.
Yes.
Yeah, so this might be terrible advice, but it's worth looking at the stuff in the perfect law for the way the hard lockup detector works.
Mm-hmm.
Because the hard lockup detector does reserve counters for, basically it's a fake watchdog, one-man watchdog.
Mm-hmm.
As a way of doing that dynamically, where this counter is reserved for somebody external to me. So you may be able to do it more dynamically using whatever mechanisms that uses.
Okay, I'll look into that. Thank you. Yes. So Will pointed out a specific mechanism in the perf core that allows counters to be reserved so the host perf doesn't use that. And he stated I may be able to handle the counter allocation more dynamically than setting a boot time parameter. Okay. Any more questions? All right, I think that's it. Thank you all for coming to my talk.